Hello and welcome to the Learning Square. In this video tutorial, I will talk about watermarking using the discrete cosine transform in Matlab. Now, watermarking is generally used to embed certain information that we want to hide in our image while transmitting. So while transferring my image over the net, I don't want anybody else to decrypt that image and read that information which is hidden inside that image. So visually the image is not distorted very much, but the information is hidden. So let's see how we realize it using Matlab. I have the code written for you here. I'll just go through it line by line. So we start off by clearing all the variables, closing all the images. I read the image greens.jpg, which is an inbuilt image in the Matlab, and I just see it. Now what I do is I store this image in a variable y, where y is in the double format of the image that I have read. Now I start off by assigning A to a matrix of all zeros. The size of the matrix would depend on the size of my image that I am reading. So here this is a 300 cross 500. So I have taken it as 300 cross 500. Now essentially you can see if I run this, so that's my greens image, and this is the image that I have created here. So I start with A, zeros 300 cross 500. I assign 100 pixels to 250 in the X region as white and 100 to 350 as again white in the Y dimension. So I see this image, this is a rectangle. I want to save this image in my green image. So I store it as a m.data file. So this is how I can store my A image as the m.data file. Now I will perform the watermarking. So what I do is I assign the RGB components of my X here to x1, x2 and x3 variables. I perform the discrete cosine transformation on each of these RGB components, and here I am just storing these as other variables dx11, dx22, dx33. After performing the discrete cosine transformation on each and every RGB component, I load my M data, which was basically the rectangle that I had created. This is the binary mask for watermarking. Now I have assigned the coefficient of watermark strength here, which is 10 here. I can change it, and I assign RM as CM as the rows and columns for the size of M. That's my 300 cross 500 which we had taken. Now I assign here the dx1, that is the red component of the image. I take it as the original one right from the rows to the columns, and I add a factor of G, that is 10, to that image here. So I am multiplying G and I am adding the data here, which is the M data. So effectively across the rows and columns I am just adding this data. Similarly for the green component I do the same thing, and for the blue component I also do the same thing. So my RGB components are changed. This is how they look like. So this was my original image. This is the image that we had seen here. This is the mask that I had created, and this is how my dx1 would look like. This is how dx2 would look like, dx3. Now once this is done, I perform the inverse discrete cosine transform. These are inbuilt functions, idc2 to do the inverse discrete cosine transformation and dc2 to do the discrete cosine transformation. So I perform the inverse discrete cosine transformation on each of these variables now, dx1, dx2 and ds3. So once this is done, this is how I see my results. So this is how these look like. I can combine them together to see how my y looks like. You can see here in the variables, y is basically a type double. To be able to visualize it properly, I will have to divide it by 255. So this is how my image would look like after dividing by 255. So effectively my image really does not change much. I can't really decipher that there is an image which is watermarked inside this, and this is how my original image looked like, and this is pretty similar to this. And if I want to see the difference, I have the absolute value of y minus x, and I have scaled it to by 100 to see how the difference looks like. Now once this is done, I then want to do the de-watermarking. For this, what I do is I take the original image and I perform the discrete cosine transformations on again the RGB components of my y image. Y is basically this image that we had created. Once I do the discrete cosine transformation on this RGB components, I again subtract the values from the RGB channels separately and store them as dy1, dy2 and dy3 respectively. Now I perform the inverse discrete cosine transformation on all of these to be able to get back my original image, and I assign this to the YY image. So my entire red component, green component and the blue component are now assigned to these inverse discrete cosine transformations of each and every channel. Now this is the combined image YY, and this is also a double, you can check it. So I just see this using the IMShow YY divided by 255 to be able to see whether my values have actually changed from the original image. I subtract each and every value and scale it by a large factor to be able to see any kind of difference which is occurring after this de-watermarking. So this was my image which comes after, this is YY by 255, and this is black. So it means everything is 0, so there is no difference once I have done the de-watermarking in this image. Now we can change this factor, maybe take it to 100 and see how my images look like. So again, not a very significant change in the image. Let's make it larger by a factor of maybe 1000. So here you can start seeing now that this watermark is changing my image. It's pretty visible now. This watermark is now visible. So as I keep increasing the factor, the image will start getting distorted and the watermark will be visible. So you can just see for yourself, play around with the code. This brings us to the end of this lecture. I will see you in the next one. Thank you.